A new telescope lifts off to separate alien worlds from their stars. Our own sun reminds us it's anything but quiet. NASA inches closer to quiet supersonic flight over land. And Webb flips what we thought we knew about how black holes feed. Pandora lifts off, a new way to separate exoplanets from their stars. This week, NASA quietly opened a new chapter in exoplanet science. On the morning of January 11, 2026, the Pandora spacecraft lifted off from California, beginning a mission designed to solve one of the hardest problems in studying distant worlds, telling planets apart from their stars. Pandora launched aboard a Falcon 9 from Vandenberg Space Force Base, alongside two CubeSats, Black Cat and Sparks. The launch was nominal, and the mission is now underway. Here's the challenge Pandora is built to tackle. When a planet passes in front of its star, a transit, only a thin sliver of starlight passes through the planet's atmosphere. That light can carry chemical fingerprints like water vapor or oxygen. But at the same time, telescopes also see the rest of the star's surface, which is anything but calm. Stars have spots, bright regions, and activity that can mimic or hide the very signals astronomers are hunting for. The clever part is Pandora's approach. Instead of short snapshots, it performs long, steady observations, about 24 hours at a time, watching the star before, during, and after each transit. It measures visible and near-infrared light simultaneously using a 45-centimeter aluminum telescope and a near-infrared detector originally built for the James Webb Space Telescope. That combination lets scientists track what changes with the star and what changes with the planet. Think of it like listening to a duet and finally being able to mute one singer at a time. During its one-year prime mission, Pandora will closely study at least 20 exoplanet systems, many first found by TESS. The data will be public, and the goal is practical: make future claims about habitability more trustworthy. What to watch next? After a month of commissioning, Pandora begins its long stares, providing a new calibration tool for the entire exoplanet era. The sun is wide awake, and that changes our daily lives. Right now, the sun is doing something it only does once every decade or so: it's wide awake. After years of relative calm, our star has entered solar maximum, the most active phase of its natural cycle, and that shift has real consequences far beyond astronomy. On September 24, 2024, scientists from NASA, NOAA, and the Solar Cycle Prediction Panel formally announced that the sun had reached this peak. But the signs were already unmistakable: sunspots multiplying, flares flashing, and eruptions rippling across the solar surface. Here's the key idea: the sun runs on magnetism. Over roughly 11 years, its magnetic field twists, stresses, and eventually flips, north and south swapping places. During solar minimum, that field is relatively orderly. During solar maximum, it's tangled and unstable. And when magnetic fields snap, energy is released, sometimes explosively. This is where the Solar Dynamics Observatory becomes essential. From its orbit around Earth, SDO watches the sun continuously in ultraviolet light that never reaches the ground. Using its 171 angstrom filter, scientists track the sun's corona and the glowing magnetic loops that act like loaded springs before they release energy as flares or coronal mass ejections. Think of it like weather on Earth. Calm skies don't tell you much. Storms reveal how the atmosphere really works. So why should anyone outside a space agency care? Because solar storms don't stay at the sun. They can shake Earth's magnetic field, disrupt radio and GPS signals, degrade satellites, expose astronauts to radiation, and, under extreme conditions, strain power grids on the ground. This isn't science fiction. It's happened before. But there's a flip side. Solar maximum is also when we learn the most. Every flare improves space weather forecasting. Every eruption helps engineers design tougher spacecraft. Every storm sharpens our ability to protect modern technology. What to watch next isn't a single event, it's a heightened era. More flares, more auroras, more moments when the sun reminds us that even from 93 million miles away, it still has a say in daily life on Earth. NASA's quiet supersonic jet is past first flight. Now, the real test begins. Let's ground this for a second. The first flight of NASA's X-59 happened back in October. That flight wasn't flashy. No sonic boom, no Mach numbers. Just a careful, methodical check that the airplane actually flies the way engineers promised it would, and that's exactly why it matters now. X-planes don't exist to impress on day one. They exist to earn trust, slowly. That first flight was NASA saying, okay, the models were right, we can move on. Here's the human part. This aircraft is deeply weird. The nose is so long the pilot can't see straight ahead. There's no forward window. Instead, the pilot lands using cameras and screens, basically flying a real-world jet like a high-stakes simulator. The engine sits on top of the airplane to shove noise upward. Every design choice is there for one reason: control how shock waves hit the ground. Because sonic booms are the real enemy. Right now, supersonic flight over land is effectively banned because it's loud and disruptive. The X-59 is trying to answer a simple question with huge consequences. What if breaking the sound barrier didn't sound like breaking anything at all? What's happening next is the part to watch. The aircraft will start pushing faster, eventually going supersonic, and then, this is key, it will leave restricted airspace. NASA plans to fly it over real towns, real people, real homes, and ask them what they heard, not what instruments recorded, what humans noticed. If this works, it could reopen an entire category of flight that's been closed for half a century. Faster travel, over land, without rattling windows or trust. The hard part isn't flying fast anymore. It's flying fast without being annoying. NASA's James Webb Space Telescope has just delivered one of its most surprising black hole results yet. And it comes from a galaxy practically in our cosmic backyard. The Circinus galaxy, about 13 million light-years away, hosts an actively feeding supermassive black hole. For decades, astronomers thought most of the intense infrared glow near its center came from outflows, hot material being blasted away from the black hole. Webb just showed that idea was backwards. Using a cutting-edge technique that turns Webb into an infrared interferometer, essentially making it behave like a telescope twice its size, scientists produced the sharpest infrared view ever of a black hole's immediate surroundings. And the result is striking. About 87% of the hot dust emission is actually coming from material falling into the black hole, not blasting away from it. Think of it like finally seeing whether smoke around a fire is drifting away or being sucked straight into the flames. This matters because it changes how scientists model how black holes grow, how they affect their galaxies, and how energy flows through galactic cores. Even more exciting, this technique can now be used on other nearby galaxies, potentially rewriting what we think we know about active black holes across the universe. Webb didn't just sharpen the picture, it changed the story. Thanks for watching This Week in Space here on Wormhole to Cosmos. If you enjoyed this episode, give it a thumbs up. It really helps the channel grow. Subscribe if you haven't already, and hit that new hype button to let us know you want more stories like this every single week. Wormhole to Cosmos exists because of you. Your curiosity, your comments, and your support make this possible. Thank you for watching, and thank you for being part of the journey. Remember, the universe is vast, mysterious, and full of wonders waiting to be explored. stay curious, keep looking up, and until next time, keep your eyes on the stars.